So we're going to encounter a measurement problem when trying to express the size of an AC quantity. How do you grant a single measurement of some meaningful magnitude to something that's constantly changing? We've got these periodic functions that are changing values all the time. How do we kind of try to capture that information in one widget or one data point? Because the voltage and current values of AC systems vary periodically with time, several different values can be used to define the amplitude. These are the peak value, the peak-to-peak value, we've already talked about these, the instantaneous value, the average value, and something called the RMS value. The peak value, also called the peak voltage or the peak current of an AC sine wave, occurs twice each cycle, once at the positive maximum value and once at the negative maximum value. So here we show one cycle of an AC waveform. We see that it reaches a peak value once and it reaches a minus peak value a second time. And this is the magnitude of the voltage or current between the peak positive and the peak negative here is called the peak-to-peak value, as we show here. So the distance from the positive maximum to the negative maximum, the peak-to-peak value. And we can call that the peak-to-peak voltage or the peak-to-peak current. The instantaneous value of a waveform is the value at any time. It can be anywhere from 0 to the peak value. Here we illustrate a couple instantaneous values at 90 degrees and 150 degrees and at 240 degrees. So we see we've got some sort of sine wave. At 90 degrees it is 100 volts. That corresponds to the peak value. At 150 degrees, we see it as less than 100 volts. It's decayed down to 50 volts. And at 240 degrees, it's negative 86.6 volts. So the instantaneous value is just the value of the waveform at any given specific time. The average value is a little trickier, right? The average value is sometimes, but not very often, used to express the mathematical average of all the points on a waveform into a single aggregate number. So you can see what it's trying to do. We had all these instantaneous values, we had the peak value, we had all these things, but really we're concerned more with, well, what's the average value, what's the mean? Well, if we have a sine wave, and we try to do this, we would call this amplitude measurement of trying to average all the points together, we would call that the average value. Although this technique is used in other disciplines of electrical and computer engineering technologies, it's not really commonly used in power systems, because for a pure sine wave centered on the x-axis, if we average all the points above the x-axis and all the points below the x-axis, so if we were to just calculate, if we were to integrate over that sine wave and then continue to integrate over that sine wave, well, what will we get? We would get 0, right? The average value of the AC waveform centered along the x-axis is 0. So if we just took the average value of a sine wave as representing some general property of the sine wave, we would just not have any voltage or not any current, right? So that's clearly not a very useful form of measurement for us. A practical measure of a waveform's aggregate value is therefore usually defined as the mathematical mean of all of the points' absolute value over a cycle, meaning we calculate the practical average value of the waveform by considering all the points in the wave as positive quantities. So this is a more practical solution here. What we've done is we've just taken the absolute value, and we can see that if we take the average of all the points, if we just take the absolute value of them, now it's a non-zero quantity. Right? So that might be a more useful term. What if we just took the average value? What if we just integrated? What if we did the integral from 0 to t of x of t dt? So that would add all this stuff up. Right? That would add all the area under the curve. And then what if we divided that whole function by the length of a period? Now we get the average value of the waveform considering everything being positive. So we're getting someplace. That might be a little bit more useful. Unfortunately, all of these measurements of average values can result in some misleading results when comparing two different types of waves. So for example, a square wave peaking at 10 volts obviously has a greater amount of voltage for a longer duration of time than this triangle wave here that also peaks at 10 volts, right? We got a square wave, it's got a peak value of 10 volts. We got a triangle wave that it's got a peak value of 10 volts. Clearly the same amount of voltage or energy is not being delivered by the triangle wave as it is by the square wave. And the effects of these two AC voltages powering a load would be very different. So what is an engineer to do? Clearly we need a measurement that allows us to easily compare between DC and sinusoidal sources of varying wave shapes in a meaningful way, and for that we use another term called the RMS value. So I'd be remiss if I didn't point out my artfully drawn diagrams here. Here we have 10 volts peak. It's a square wave. We see that lots of heat is dissipating from this resistor, indicated by the 3 red hot arrows coming out of it. And then if we apply a same 10 volt peak triangular wave to the same resistor, we get some kind of cool 2 little black arrows coming off of it, indicating that the triangle wave is not delivering as much power.